So the name of the code already gives away what this code is about. The code is called SONG, which stands for second order non-Gaussianity. The second order, of course, tells you that this is in contrast to class, which is a first order or linear code. In perturbation theory, we're dealing with second order perturbation theory. And the non-Gaussianity was the original purpose for that we built the code in order to compute the so-called intrinsic non-Gaussianity and to see if that would be observable by the Planck satellite mission. But after that, the code has evolved, in fact, to do much more than just compute non-Gaussianity, and is a kind of general purpose code for second-order perturbation theory. So the name could eventually be changed, but of course we don't want to change the name, so it will be called SONG forever. Anyway, the first question when we look at SONG, which essentially in a nutshell is like class, but you do everything to second order, is why do we even need second order perturbation theory? And of course, the first thing that comes to mind is with second order perturbation theory, we have much higher precision. And Julian just before told us that there are some precision files for class that will give you 0.1 per mil precision, and that these already are very slow and take hours to compute. And when we look at the perturbation theory that we do here, then this is a perturbation theory in the primordial fluctuation that we do. And the primordial fluctuation are typically of order 10 to the minus 5, which means that the second order corrections are of order 10 to the minus 10. So now if in class we only compute the first order to maybe a per mil, maybe a bit more than per mil, clearly we are not interested in correction that of order 10 to the minus 10. So for the purpose of precision, this is completely redundant. Then one can say, okay, this is for the CMB. Of course, for large-scale structure, we know that the perturbation theory eventually breaks down, and we get important nonlinear corrections. The problem there is that as soon as you have important nonlinear corrections, the second order is not good enough anymore. So we would need third order, fourth order, and so on, eventually getting a full non-perturbative description. And then there remains just a tiny window of scales where the first order is still small and maybe the second order gives a relevant correction. But even there we have a problem, because when we want to compute the power spectrum, typically the power spectrum that you compute in class is the 1-1 term. So you combine two first order perturbation to get the power spectrum. And if you make a second order calculation, you get a 2-2 term where you combine two second order perturbations. But there is another correction that is of the same size, and that is the 1-3 term, where you combine a first order perturbation with a third order perturbation, and that is of the same order as a 2-2 term. So in order to get in this small range of windows, in order to get the correction to the power spectrum, we would in fact need a third order perturbation code. So really this one, higher precision, I can completely cross out. This is not at all what we are looking to compute. So then the question remains, what can we do with the code? And of course, what we are interested in is new physics, physics that you cannot capture in a linear perturbation code. Because in linear approximation, this physics is exactly zero. And if the linear order is zero or almost zero, then of course second order perturbations can become important. And as the name of the code suggests, non-Gaussianity is one such thing that you cannot compute at linear order perturbation theory. So let me explain this in a little detail here. At first order, we can take any perturbation delta. That, of course, depends on the wave mode and time. And because we make an expansion to first order in the primordial perturbation, this phi here is a primordial perturbation, we know in any time you do a first order perturbation, the first order is just given by the perturbation times the expansion coefficient. And this expansion coefficient here we just call transfer function. And in general, the expansion coefficient can depend on k and tau. So on the mode that you're looking at and on time. Primordial perturbation, of course, does not depend on time. It's just your initial conditions. And then what we also see here is that the k doesn't have a vector. This is not a mistake, but it follows from the isotropy and homogeneity of our universe. So we make the assumption that in our universe there is no preferred direction, which means that all of the preferred directions that we have in the realization of the universe come from the random field, the primordial randomness in the universe. This is absorbed here. These functions are just mathematical objects that simply tell us about the general structure of the universe after we have removed all of the perturbation. So this one cannot have any direction dependence. So it only depends on the magnitude of k. And then what we see here when we look at this equation from this point of view is an extremely nice split into the statistical and non-statistical quantities. We know that our perturbations here, they are statistical, so they depend on the random initialization of our universe. This primordial seed here is also statistical, but the transfer function that we're looking on here is completely non-statistical. It's just a function that you can compute independent of your actual primordial perturbation. And this, of course, is very useful because when we, for example, run class, we don't have to run class for a number of different initializations. We just run class to compute this transfer function here, which is not statistical anymore. So class does not solve any stochastic differential equations, but just ordinary differential equations. So why is all of this important? It is just if we want to look at the statistic of our perturbation, and we know the statistic of our initial seed. Then in linear order perturbation theory, we see quite clearly that the statistic of the perturbation is the same as the statistic of the seed because it just gets transported with a function that is non-statistical. Or in other words, if our primordial perturbation is Gaussian, then all our perturbations are Gaussian. And that means that whenever we make a measurement and we see that our perturbations are non-Gaussian, in linear theory, we would follow, if this is non-Gaussian, then our primordial perturbation is non-Gaussian. And this, of course, is interesting to know for theories of inflation. So this is kind of the goal that we want to do. We want to learn something about our primordial perturbation. We look at the actual perturbation, and from there we try to infer the statistics of the primordial perturbation. And so far, of course, we all know that the perturbation that we see in the CMB are almost perfectly Gaussian. Up to the precision, we have not found any non-Gaussianity in there, apart from some lensing effects, but let's ignore this for now. So what we have is that this is almost perfectly Gaussian, so we follow that this is almost perfectly Gaussian plus a small correction. And this is the story at linear order. But if you go to second order perturbation theory, you get a much more complicated equation, how you relate a second order perturbation to the primordial seed perturbations. And of course, what I did here is I just write down a second order expansion. So here, because it's first order, I have one primordial perturbation. Now, because it's second order, I have two primordial perturbations. There's no reason why they should be evaluated at the same k, so I put a k1 and a k2. And then the rest of the structure is just in order to make sure that all the rotational symmetries that I want to have in the system are fulfilled. And this dictates that if I want to have two primordial perturbations, I have to multiply them with a non-statistical time-dependent kernel and do a convolution over this kernel. And after I do that, I get my second order perturbation. So the equation looks a lot more complicated, but what is important to see here is if I make the assumption that my primordial perturbation is perfectly Gaussian, then these two are perfectly Gaussian, but the statistic of my second order perturbation is now a convolution over two Gaussian perturbations. And in general, a convolution over two Gaussian perturbations is no longer Gaussian. And this is not something where I have to select a specific shape for this second order transfer function here. This is a very general statement. So non-Gaussianity of this second order perturbation is not something that can arise at second order in perturbation theory. It is something that naturally always arises in second order perturbation theory. So all of the higher order terms will be non-Gaussian no matter what we put here. If this is non-Gaussian already, of course, this will also be non-Gaussian. But if this is Gaussian, this is still going to be all non-Gaussian here. So this means now, if we want to look at an experiment that measures perturbations that are non-Gaussian, we have to ask the question, are the perturbations non-Gaussian because of the second order correction that we have to the perturbation, or are they non-Gaussian because the primordial perturbation is non-Gaussian? And in order to answer this question, we cannot do linear order perturbation theory, because at linear order perturbation theory, we have this trivial relation between the statistics of the perturbation and the statistics of the source. So we really need to go to second order, do this calculation from the assumption that we have mostly Gaussian plus small perturbation initial conditions. We compute the induced non-Gaussianity, which we call the intrinsic non-Gaussianity. And then we can look if we find this intrinsic non-Gaussianity in the experiment, or if we find more, then it means that this also has to be non-Gaussian. Okay, so this is one of the possible applications, and this is in fact what we have developed the code song for. But there are much more that you can do with the second order code. So for example, the second thing is here mode coupling. In linear order perturbation theory, what we see here is that the transfer function t is just a function of k. And of course, you cannot write down anything else, because as soon as you try to write down anything else, you would necessarily have to involve a second perturbation, which would make it second order. And this means that at linear order perturbation theory, when you look at your perturbations in the universe, you can decompose them into individual wave modes, and then each wave mode evolves completely isolated from the rest of the universe. So you can just select one wavelength, evolve that wavelength, independent of whatever happens in the universe apart from that wave. So there's no coupling between modes. At second order, what we have written down here, the second order transfer function is precisely a mode coupling term, which tells you how you can combine a Fourier mode K1 with a Fourier mode K2 to form a new Fourier mode K. And of course, there are some rules that are dictated by the rotational symmetries of the system. But second order also naturally always generates mode coupling. And of course, mode coupling is something that is very interesting for different things. What is of course well known, we don't compute this in SONG, is for example the bias, where you look how a small scale perturbation evolves in a long wavelength modulation. At linear order, you don't get any of this. So you need to go to second or higher order in order to compute any physics that depends on mode coupling. Then the next topic, which we actually do compute in SONG, is a scalar vector tensor coupling. It's very similar to the mode coupling that you see in this equation here. A scalar vector tensor coupling, again, you cannot read it from these equations because I didn't want to make them too complicated. But in first order perturbation theory, you have not only that all Fourier modes evolve independently, but all of the magnetic moments evolve independently. So you have scalars, scalars can only couple to other scalars, you have vectors, vectors can only couple to other vectors, and so on. At second order perturbation theory, this is also broken. You can write down terms that couple scalars to vectors or scalars to tensors. And the reason is that here there is a certain geometry in this configuration. So scalars are defined with respect to one preferred direction. And at first order, the problem has only one direction. So we can just define our scalars with respect to this direction here. But here we have geometric couplings which depend on two directions. And what is a scalar for the first K1 is not a scalar for the second K2. So very naturally, you can write down terms where scalars source vector and tensor perturbations. And this, of course, is interesting because we know that in the CMB, there's one particular type of polarization. So Julian talked about this a bit. When you have the polarization, you can decompose it into two modes, the E mode polarization and the B mode polarization. And the B mode polarization has a special property, and that property is that it cannot exist for scalars. So it only exists for vector and tensor perturbations. And this is the reason why when we look at the CMB, what we observe is that we measure the temperature perturbation, we measure the E mode perturbations, but we don't measure any B mode perturbations or any B mode polarization. And this tells us that tensor modes in our universe are strongly suppressed, and the universe is really dominated by scalar modes. At second order, when we do this computation at second order, we can have a universe which is dominated by scalar modes, but the scalar modes couple to form vector and tensor modes, and the vector and tensor modes induce B mode polarization. So if we look at the B mode polarization, again, we have to ask ourselves, is this B mode polarization a consequence of having tensor perturbations at first order, or is it a consequence of simply an intrinsic mode coupling that happens inevitably at second order in perturbation theory? So this is also something that, of course, is very interesting to look, and you need to do a second order computation in order to be able to understand these observations properly. And finally, what I want to talk about here, which is very important, are source terms. The first order equations are very special because they have a property that they are completely source-free, which means that you specify the initial conditions, and from the initial conditions, you can simply evolve your system forwards in time. There are no driving terms, no forcing terms, no external forces that would act on the evolution of the perturbations. Of course, all the perturbations are coupled with each other, but there are no source terms in the system of differential equations. And this changes at second order, and is due to the way how one writes down the perturbation series. So at second order, when we look at the differential equation for these second order perturbations, or because we want to remove the statistical part, we look at the evolution equations for these transfer functions that now depend on k, k1, k2, and tau. So they're much more complicated than at first order. But if we look at the evolution equation of these functions, we find differential systems that are quite similar to the first order ones, but they have sources. And these sources are composed of quadratic products of two first order perturbations. And this means that when we solve these equations, even if we have zero initial conditions in the second order system, because we have first order perturbations, they will source the second order evolution and you will get second order perturbations. And why is this interesting? And this is interesting, for example, for terms that at first order do not have any sources. So for example, at first order, we can write down evolution equations for magnetic fields. And the evolution equation for a magnetic field is relatively boring because the only thing that happens to a magnetic field is that it is diluted by the redshifting of the universe. So if we have any magnetic fields, they will just be diluted away and there's no source for them that would come and induce them. But at second order in perturbation theory, when we write down the equation for a magnetic field, it is still diluted by the Hubble expansion, but we get a lot of quadratic terms that can source magnetic fields. And now suddenly at first order, the magnetic fields decay. At second order, we have terms that can later in the universe induce magnetic fields. And this way can generate magnetic field power spectra. Okay, so these are the main differences between first order and second order perturbation theory and some of the applications that we can be interesting to look at using a second order perturbation code. Now I want to give you a very brief history about the development of the second order Boltzmann codes. So as already mentioned earlier, the initial idea was to look at the intrinsic bispectrum. This is the bispectrum that is inevitably induced from the second order dynamics, and to see if that intrinsic bispectrum would be detectable by the Planck satellite mission. And of course, this is an important question that we need to solve before we can really understand, if we measure any non-Gaussianity with Planck, what that really means. So in order to solve this question, there were a couple of codes developed. This one I call the first generation codes, and these three the second generation codes. The first one was the CMB Quick, which was developed by Cyril Pitrou in 2011. And the code was completely written in Mathematica. And because it was completely written in Mathematica, it was unbelievably slow. Initially, it took a couple of weeks to make one computation to get the intrinsic bispectrum. And the interesting part is that this code, CMB Quick of Pitrou, produced a result that would be observable by the Planck satellite mission. So after seeing this, we were all very excited that there would be a signal that one can find with the Planck mission. And of course, we wanted to cross-check this code. And in fact, 3 groups started to develop second-order codes to verify and cross-check this result. And the first code that was released was by Huang and Vernizzi in 2012, which was an implementation in C++ called Cosmolib. And this code was significantly faster than the CMB Quick. And instead of a few weeks, it takes a few hours to run, which of course makes a huge difference if you want to check the code, make sure that all of the integrations are properly converged. Because if your code already normally takes a few weeks to run, you can't really do too much analysis on the convergence of your code. Then shortly after that, we have released the code Song, which is coded in C and is directly based on class. So the code Cosmolib is a completely independent code that is written from scratch. And of course, in order to do a second order computation, you need to also do a first order calculation first. So the structure of the code is always you first solve the first order equations, then you solve the second order equations, because you need to solve first order equations to compute the quadratic sources that drive the evolution of the second order perturbations. And for this, also in Cosmolib, there's kind of an independent first order code in Cosmolib that will then be called by the second order part of Cosmolib. We decided on a different strategy, and we used the already existing class code to do all of the linear calculations. And then we have built the code song around the class code. Also, the code song, in contrast to the other codes, was extended a lot to not only compute the temperature bispectrum, but also include polarization, magnetic fields, and many other quantities at second order. And then finally, there was a third code by Su and Shellard, which is not publicly released. It's not known if they have a name for it internally, but if it has a name, we don't know it. Anyway, this code also is in spirit relatively similar to the Cosmolib, and has all of these codes have kind of similar run times of a few hours. And then what we did is we compared the results of all these codes very carefully, found some bugs in essentially all of the codes. But after we have done some comparison of the results, eventually we found some output that really agreed within the three codes. And the problem, or maybe not a problem, but what we found was that the result was significantly smaller than what was predicted by the CMB Quick, and was no longer detectable by the Planck satellite mission. So let me talk a bit about the most important features of the Song code. Song is based on the class code, which I already mentioned. All the linear calculation and also the calculation of the background perturbations are just done by class itself. And then we have built a second order part, and we have not just built a second order code around the Song, around the class code. We have built a code in such a way that we have asked ourselves the question, if class would have a second order part, how would it look like? So we have developed a second order part using the same coding spirit, using the same naming conventions that are also used in class, and using the same structure of the code. In particular, because class is modular, that has a number of self-contained modules, we have kept this structure exactly. So Song is built very closely to class, has different modules that are completely self-contained and can be called that solve a certain physical, well-defined physical task. And really, it is not a code that is built around class, but it's kind of more of an extension of class to do second-order computations. The code is also relatively easy to learn, where easy here, of course, has to be taken with a grain of salt, because it is a second-order code, which has huge equations implemented in it. So it is not easy in that sense, but it is relatively easy for a second-order code, because we have made a lot of comments in the code. We have documented all of the functions very well. And again, because it is based on class, that means that if you have some understanding of class and you read the Song code, you will find a lot of the things that you already know, and you can connect to the calculation much easier than if it would be a code that was built from scratch. Then the code is also very fast and efficient. In particular, there is the integration for the bispectrum, where there are different approaches how this multidimensional, highly oscillatory integration can be done. And we have developed a method that by transforming the quantities to the variables, map the highly oscillatory degrees in one dimension only, and that helps a lot with the integration. So after all, it then takes about 8 hours on a single core to run the codes to get a good precision output. And that is essentially the same as the other second order, second generation codes. Okay. Now let's go a bit more into detail. The version of class that is within the code Song is not the standard version of class, but it is a modified version of class. And it has to be a modified version of class because we need some additional outputs. Usually when class runs the code, it will store the line of sight sources. But for a second order code, we don't just need the line of sight sources. We in fact need to store all of the first order transfer functions and build quadratic sources from them. So we have just modified the class code such that the code will now, instead of producing just a line of sight sources, will fill big tables of sources from the first order perturbations that will then be read into the Song part of the code. In addition, we have 2 extra modules. We have added 2 extra modules to the class code. And the first one is called a bispectra.c. And this module takes a primordial perturbation, a non-Gaussian primordial perturbation, and then computes the resulting linear bispectra from that primordial non-Gaussianity. And why do we need this? is typically when we compute the intrinsic bispectra, we get output that depends on three, how are called, three multiple moments L. So the bispectrum can be visualized as kind of this tetrahedral shape, but it's very, very hard to put that into a number. So typically when we do experiment, we want to have simple numbers. And in order to reduce the bispectrum to a simple number, what one usually does is one compares it to some predefined primordial templates. And in order to compare it to these primordial templates, of course, we have to compute how the bispectrum of these primordial templates looks like. And this is why we have added this bispectra.c module to class that does exactly that. And it does it for any type of primordial kernel that you want, separable, non-separable, it doesn't matter, can do all of them. Then we have another module which is called Fisher.c, and Fisher.c does exactly the comparison of the different templates with the intrinsic template to produce the numbers of FNL contamination, signal-to-noise ratios, and so on. And what I want to stress here is that these modules here that we added are needed to run the song code, but if there may be some interest in using them, even if you are not interested in doing second-order perturbation theory. So if you have some primordial kernel from some theory of inflation and you just want to see what kind of bispectrum you generate, you can just use the class version that is contained in Song and use the bispectra.c module to compute the bispectrum that results from such a kernel. Okay, then apart from the linear code class that is in the Song code, what we have is a number of second-order modules. And these second-order modules correspond quite directly to the first-order modules. So for example, in the first order, we have perturbations.c, and perturbations.c simply evolves the Einstein-Boltzmann system from the initial condition to a later time by solving the differential system. And now what we have in the Song code is a version that is called perturbations2.c. And it does exactly the same thing, only that it does it at second order in perturbation theory. And then, of course, in class we have transfer.c, which solves the line of sight integration, and in Song we have transfer2.c. So there's a direct correspondence between the class modules and the Song modules. And if you want to understand what Song does in a nutshell, you can kind of say running this perturbations2.c module, for example, is just like running class, only with 2 extra loops. And the reason here is, again, shown in this equation down here. In class, you compute the transfer functions, and they just depend on k. So let's say you want to have a good sampling of k values, and you do it for 100 values of k, which is actually not that good, but let's just assume you do it for 100 values of k. Then you will solve the differential equation 100 times, once for each of the k modes. Now here in second order, we have a function that depends on k, k1 and k2, and there's still vectors here, but in fact it turns out that due to this delta function and some rotational properties, one can reduce it into a function that only depends on magnitude k1, k1, k2, and an angle, which is typically not important. So we can reduce this into a function that depends on 3 k's. And now again, if we want to have an acceptable sampling, we put 100 points each. Now we have a grid of 100 times 100 times 100, which means we don't have to solve the differential system 100 times, but 1 million times. And that is one of the main reasons why the code takes much longer to run than the class code. But this is a bit too simplified to say it is just a running class with 2 extra loops around it, because of course we have some complications. We have the quadratic sources that are not present in the first order perturbations. So we also have to, in addition to solve it 1 million times or significantly more often than what you do in class, we have to feed all of these quadratic sources into the evolution. And finally, we have the geometric mode couplings, which means that this object here describes a geometric shape of taking 3 k's that then add up to form a closed triangle by this delta function. And I already told you that the geometry dictates how you can mix scalars, vectors. So in the code, there are a lot of coupling coefficients between different perturbations that depend on the geometry of this kernel here. And of course, in class, there is no geometry. You have just 1 k that you select, and there's no geometrical information at all. Then, after we have solved perturbations2.c and transfer2.c, we have the perturbations at the present time, and now we have to do the integration to get the intrinsic bispectrum, which is done in bispectra 2.c. And in this integration, what you do is simply you take the perturbations and you integrate them over this multidimensional Bessel integration, which is done in bispectra 2.c. In addition to this, there are some other modules also, which I haven't put on the slide. For example, there's one module called Spectra 2.c, which simply computes power spectra. There's a module called Bessel 2.c, which computes some geometric coupling coefficients. But this is kind of the main structure of the second order code. So in a nutshell, is doing class with 2 extra loops and some additional complications. Then let me show you what kind of results we have gotten from running the song code. And this is probably the most important result that we have obtained with the code. And what it shows here is a signal to noise for the intrinsic bispectrum. So this number just tells you if you have this intrinsic bispectrum and you design an estimator that perfectly estimates this bispectrum from the data, can you find it above the noise level that you have for this shape of bispectrum? And of course, what you want is that signal to noise should be larger than 1. And then in the different colored lines, you see different experiments where we have a perfectly cosmic variance limited experiment in black, Planck in blue, and then some core or prism type experiments in green or red. And the solid lines are including the information of polarization, and the dashed lines are only including temperature perturbations. And what we see here is when we look at the blue line of Planck, that for temperature we are cosmic variance limited up to 1,500. After that, we still add a bit of information before the line flattens out, and we come out at a signal to noise of about 0.3. So the temperature bispectrum that is induced from second order perturbations cannot be measured above the noise level with a Planck-like experiment. Then we can add polarization to this, and we see that for polarization, almost immediately, we are not cosmic variance limited, because Planck is not very good at detecting polarization. The polarization still adds some information, and including polarization, we have a signal to noise of about 0.5. Still not enough to find some detectable bispectrum. But because polarization actually is quite important for the intrinsic bispectrum, we see that polarization is not a small correction, but in fact contains more information than the temperature. So if we get an experiment that can actually measure polarization to better accuracy, for example, a prism type experiment, which is almost cosmic variance limited for polarization and temperature up to a multiple of 2000, then we get some extra information here. We come out at a signal to noise of about 2.5. So in this case, this intrinsic bispectrum will be detectable above the noise level. Then what we can also compute is not only CMB perturbations, but we can also look at other types of perturbations. For example, here we have meta-analysis, which is more interesting for the large-scale structure. And what we are looking at here is the Fourier kernel of cold dark matter and baryons. And we look at a specific configuration where we have put 2 vectors k to be equal, and the last one to be extremely small, 10 to the minus 5. So when we go into this direction here, where this k, which corresponds to this and this entry here, is larger than 10 to the minus 4, these are kind of squeezed configurations where one of the legs in the bispectrum is extremely short. And what we show on this plot here is the bispectrum of the cold dark matter, the bispectrum of the baryons. The red line is an analytic approximation that is only accurate in the large scale limit. So the fact that it diverges here is not because the code is doing something wrong, it's just because the analytic approximation is not applicable in this range. And what we see here is that in the early universe at Z around 500, what we find for the baryons is that they have the strong acoustic oscillations. For cold dark matter, we see that there's a much smoother bispectrum. And then as time progresses, the acoustic oscillations are imprinted in the bispectrum of the cold dark matter. And then at the final time, what we measure are here acoustic oscillations in the bispectrum. So these are not acoustic oscillations that show up in the power spectrum, but acoustic oscillations in the bispectrum, in a squeeze limit bispectrum. Then I also mentioned this when we can also use song to compute magnetic fields. And this plot here shows magnetic field strength over time in scale factor. And the different lines correspond to different scales. And what you see is that the magnetic fields, they are diluted as soon as the mode enters the horizon. So this mode enters the horizon here, and then the magnetic field strength is just diluted. This mode enters the horizon a bit later, this again later. But up to this point, nothing special happens. Just the magnetic field entered the horizon, and then it's starting to decay due to the Hubble expansion. But then what we see here is around the time of recombination, we suddenly have a strong boost in the amplitude of magnetic fields. And this is precisely because at this time we have these nonlinear quadratic source terms that appear in the second order equations, and these can now drive the magnetic field up during the dynamics of recombination. And then after recombination is finished, we see that the magnetic fields return to their normal decaying evolution, and the sources for the magnetic fields vanish again. Of course, this kind of calculation also you cannot get from a linear code. You really need to go to a second order code because the quadratic sources are fundamental to boosting up the magnetic field strength around recombination. Okay. Then here, this is something very exotic that we have computed. What we show here is, in fact, spectral distortions that are sourced at second order, but not just spectral distortions, but spectral distortions of polarization. So I don't know if a lot of people even know that this is possible, but you can have spectral distortions in polarized spectra. And what we show here is computed with SONG, the power spectrum of E-mode spectral Y distortions, the correlation of them with temperature Y distortions, and this is the kinematic Sunyaev-Zeldovich contribution just to the YY spectral distortion. All of these terms come from reionization times. And what one sees here is, of course, the spectral distortion in E-polarization are significantly smaller than the Y distortions, but it's extremely hard to generate these spectral distortions for polarization, so there are not many foregrounds that can give you spectral distortions in polarization. So with good enough experiments, this should eventually become observable, that you have some spectral distortions that are also induced from the second order dynamics. And then finally, what we can compute with the code, this is slightly more complicated, are late time effects. And late time effects are very problematic for the code for the following reason. If you have the early time sources, I should start a bit before. We in second order, we have the quadratic sources. And these quadratic sources have the problem that they exist at each multiple. At first order, what we have in the line of sight integration, and Julien has shown this, are just three source terms, the S0, S1, and S2, and that's it. There are no additional source terms. It's not a simplification that we are not considering S3, S4, and so on. They simply don't exist. So the entire line of sight sources are given by just three multiples. At second order, because we have the quadratic sources, this is no longer true. Instead, what we see is that we find line of sight sources at each multiple. So we have an infinite hierarchy of different line of sight sources that we have to, in principle, integrate in the line of sight integration. Of course, one cannot do this. This would be far too expensive. So we have to introduce a cut. And this cut is very simple to introduce for sources that are located at an early time. Because in the very early universe, when we still have strong photon-baryon interactions, we are in the tight coupling limit, and the tight coupling limit suppresses all the higher multiples. So in the tight coupling limit, we simply don't have large multiples. So there's a natural cut in this hierarchy. Then after the tight coupling ends, it takes a certain amount of time to generate the higher multiples at first order, so we still don't have the quadratic sources for the higher multiples. And typically, then we find that for the recombination type sources, which are very important, of course, for recombination type sources, we can typically cut this line of sight integration at something like 15 sources instead of the 3 sources that are used in class. So we have a sum over 15 different sources. But if we go to late-time sources, we know that the multiples of up to order 2000 are excited today, or even higher multiples, but up to 2000 we have enough power to be relevant. So that means that we would have in our line of sight integration 2000 sources. And for a code that is already significantly slower than a class, that doesn't take seconds but hours, now when you again get a huge factor from your line of sight integration, this can become unfeasible. And it gets even worse, because for the line of sight sources that extend over all of the time region, at first order there's only the integrated Sachs-Wolf effect. That's the only source that has a late time support in the first order line of sight integration. But the integrated Sachs-Wolf is a very smooth term. So you don't need to compute many points in time to describe it very well. But the quadratic sources that have support at late times, they are not smooth at all. So they are typically the combination of one metric perturbation, which is smooth, combined with one photon perturbation, which is not smooth, which is highly oscillatory. So in fact, we have 2000 sources that are all highly oscillatory and need a very precise time sampling. And this with a code that without all of these complications takes hours. So in practice, it is not doable to do late time sources in the code. And there are some late time sources that clearly are important. The first one is lensing. Everyone knows lensing. And at first order, there is technically no lensing, because lensing describes how a perturbation is bent by a gravitational potential. So lensing describes the interaction between a perturbation and a gravitational potential, which itself is a perturbation. So lensing fundamentally is a second order term. And in Song, we have the source terms that would lead to lensing if we could compute them. But because of the problems that I just told you, in practice, we cannot compute them. So we would have to wait until there's some additional breakthrough in computer technology that make everything significantly faster. Then we could brute force compute it. But for lensing, there's another solution, because we know that we are computing lensing since many years and there's no big problem. But we are not doing it by using second order perturbation theory. Instead, we're computing lensing by making an expansion in the deflection angles. So we assume that our lensing is a weak lensing that will only change the photon trajectory a little bit. And by doing an expansion in the deflection angle, we can reformulate the problem into a problem of first computing a lensing potential and then applying this lensing potential to the unlensed perturbations. So now what we do in the code in Song is we know that there is an alternative way how we can compute lensing, and we want to use this alternative way of computing lensing. But then clearly we have to deactivate the non-converged lensing terms in the code, because if we wouldn't deactivate them, we would get some not converged result of lensing that is kind of half lensing, plus the weak lensing contribution. So we would double count some of the terms. So what we do in the code for lensing is we just look at the sources, we isolate the sources that will generate lensing, and we set them to 0. And then we say, okay, instead of doing lensing in the code, we do lensing by using the standard weak lensing approach. And this, of course, works very well. But the problem is this is not the only term. In addition, there are so-called redshift terms. And redshift terms at first order are very simple, because at first order redshifting just means that your perturbation get redshifted due to the homogeneous expansion of the universe. When you already have a perturbation in first order, you only need to combine it with background quantities, because everything else would be second order. But at second order, if we now have a perturbation, then we can, and we propagate that perturbation through space-time. We have to look at how fast is the universe locally expanding around that perturbation. So we have to look at the trajectory, how is the perturbation traveling, and then how is the universe inhomogeneously expanding around that trajectory. And this generates redshift terms that are also integrated along the line of sight and correspond to an infinite hierarchy of quadratic sources that describe exactly this effect. And we cannot simply calculate these terms by brute force approach, because it's too expensive. But for this problem, there was some analytic work done by Huang and Vernizzi, who have shown that you can reformulate a problem by a transformation of variables, which will then locate the redshift terms at the last scattering surface, plus an analytic residual that is computed by first-order power spectra. So this is exactly what we do with the code. We, instead of using the normal perturbations in the line-of-sight integration, we use these transformed perturbations where redshift is reformulated to a last scattering surface correction. And that we can include because at last scattering surface, we don't have large multiples, so everything becomes much easier. So in using this trick, we can also compute the redshift perturbations. And in fact, they are very important. If you don't have them, that you will see on the next slide, if you don't have these redshift perturbations, you will get a significantly wrong result for the bispectrum. Then there are more terms, and the last important one are reionization contributions. And again, at first order, this is very simple. At first order, you propagate photons to the observer, and each photon has a certain chance of being absorbed at reionization. But this chance is the same for each photon. So it's just a e to the minus kappa that you multiply to your perturbations. But at second order, again, you have to look where does the photon come from and how is the universe ionized in this particular patch the photon is coming from. Because the universe is now ionized inhomogeneously. It's no longer homogeneous. And again, this is a problem of a term that one cannot simply integrate. It's very complicated. But for this, we have found an analytic way how this can be rewritten. And in fact, we can show that we can rewrite this into a blurring effect that works similar to the lensing. So we compute a blurring potential that can then be acting on the first order perturbations, plus some low multiple residuals. And the low multiple residuals, again, are not a problem because we don't have to cut the hierarchy. So in fact, these low multiple residuals only go up to L equal to 3. So there's one more than at first order where you only go up to L equal to 2, but that's not a big problem. And doing this, then we have this approach of blurring, which is very similar to lensing in spirit, plus some low multiple source terms that are explicitly included in the code. And for all of this, it's important that when you have these source terms here, you deactivate them in the code, and then you find a different way of computing them, because if you would keep them activated in the code, you would just have an uncontrolled bias of your result. And the good thing is that with lensing, redshift, and reionization, in fact, we were able to absorb all of these late time effects and reformulate them so that we can really compute the full intrinsic bispectrum at a second order in the code. And here's just to show you one of the plots for the B-mode polarization that is generated here by these reionization effects, which are written here as loss and gain. The gain are the low multiple residuals, and the loss is the blurring. And then you see that these two generate some B-mode spectra that is shown here, compared to a tensor to scalar ratio from the initial class run, which will generate B-mode polarization of this order. So you see that in a range between 10 and 100, the blurring is comparable to a tensor to scalar ratio of 10 to the minus 4. While in red, we have the lensing correction, which is significantly larger. But of course, the first problem, if we want to measure such small tensor to scalar ratios, is to get rid of the lensing and to analytically treat the lensing. But if you can do that well enough, eventually you hit another bound here with the blurring. And all of the other effects are significantly smaller below this one still. So for B-modes, the two biggest contributions are lensing, and then the second biggest one is the blurring. Okay, so these are the late time effects. Then I just want to give you an impression of the accuracy that we get with song. And of course, this is very different than when you run class. So in class, your goal is to get per mil level accuracy or potentially more than per mil level accuracy. And here, what is shown here is a bispectrum, so an intrinsic bispectrum where one of the multiples is fixed at 6 and the two other are equal, and then they are normalized to some first order CL power spectra. And for this particular combination, there exists an analytical squeeze limit approximation, which is this red line here, the red dashed curve. It's the analytical squeeze limit. And analytical squeeze limit is accurate if the multiple moment L is significantly larger than 6, because otherwise we're not in a squeezed configuration. And what we see with the song, the result with song is the blue line, the blue solid line. And we see that here we are quite far off the result. But of course, this limit here is not very squeezed. So we cannot trust the analytic approximation in this limit. But the analytic approximation gets increasingly better as we move to this side of the spectrum here. And then we see that Song quite accurately describes the red curve, but in each second peak, we are kind of a bit off. So here we are, here it's actually not too bad. Here we are off, and here we are significantly off. For class, we would be very unhappy here, I would say. But for Song, really what we try to achieve is very different than in class. And there are a couple of reasons for this. First, in class, the code scales well with accuracy. Let's say you have a k-grid of 100 points. And now you say, well, my k-sampling is maybe not good enough. I just take 200 points. Now the code takes roughly twice as long to run, and you have k-sampling which is twice as good. In Song, if you want to say, well, my k-sampling is not good enough, let's just double the k-sampling. Because you have 3 k's, now the code is roughly 10 times slower, not twice as slow. And then if that is not good enough and you have to double again, the code is suddenly 100 times slower than before. So the code really scales very differently with the precision parameters than class. And this means that there is some limitation to the accuracy that you can realistically reach. In class, we know that if we want to go to sub per mil, so per mil is still relatively fast, but sub per mil, we have to take significantly more effort. And in Song, if you want to do the same, it doesn't go from seconds to hours, it goes from seconds to from hours to weeks, a month, or even years, because the scaling is much worse than in class, because of the extra grids that you have, the multi-dimensional grid that you have. So it may be that if we just take 100 times the computation power, this one will go away. It's very possible, but of course it's not realistic for us because we are actually very happy with this curve because it shows that after doing the code where we solve the differential system millions of times, then we do highly oscillatory Bessel integrations in the line of sight with a huge number of source terms. Then we fold all of that together to get a squeezed bispectrum where there's again more oscillatory integrations. What we get at the end matches this red curve extremely well. So this really shows that there is no fundamental problem in the code. And then what I also want to tell here is the dotted blue line is when you do not include this redshift term that I have shown here. So here there was this redshift term, which is taken into account with the transformation of variables. And if you do not have this term, you get this result here. Now you know that something is missing in your physics. Right? You see, okay, we get kind of all the oscillations correct, but there's a almost constant offset that I'm missing. And then by this transformation of variables, we can include this redshift term and we get the result that is sitting down here. But this transformation of variables is not so simple because, as I told you before, you want to deactivate some of the sources. But the redshift term is a line of sight contribution. But in addition to the line of sight contribution, which is computed in the transfer 2.c module, you have the perturbations 2.c module, where the same terms have a different interpretation. And in the perturbations 2.c module, which, for example, in tight coupling, there's no such thing as free propagation of photons where they become redshifted along the trajectories. This doesn't exist because you have scatterings all the time. And now these terms that are interpreted as a redshift term along the late-time evolution of the second-order system have a very different interpretation there, and we do not want to deactivate them in the perturbations 2.c module. So this means in the early tight-coupled universe, we want to keep these terms, and then later along the line of sight, we want to neglect these terms. But there is, of course, in the real universe, no clear-cut transition because how's it called? Visibility function is not a delta function. If the visibility function would be a delta function, there would be no problem. But of course, in reality, the visibility function has a certain width. And during this width, we cannot completely, on a theoretical level, consistently turn them partially off and partially on. So what we do is in transfer 2.c, we deactivate them. Perturbations 2.c, we still activate them because they describe different physics. And it's also possible that these differences here come from this treatment of the redshift term, and that there could be an improved analytical version which would be extremely complicated that maybe remove these extra effects. But it can also be that this is due to scaling of the code. But overall, really, one has to keep in mind what the goal of the code is. The goal of the code is to get a good estimate of these nonlinear effects and how they will be observable, or how they should be cleaned from CMB observations. And for this, the blue curve is giving us all the information that we need, and allows us actually to understand these terms at a precision that is much higher than what we actually need. Okay, then as a final point, before I finish today, I've now told you all that you can compute with song. So you can compute B modes, non-Gaussianity, magnetic fields, spectral distortions, all of this the code can do. In fact, whatever you want to do from a second order, the code has all of the second order perturbations integrated in it, and you can extract them all. But there are some things that the code does not compute. In particular, first, because they make the problem theoretically more complicated, or because they would make the code even slower. So we have focused on quite standard cosmology in order to really understand the bispectrum for a normal Planck model cosmology. So we have not included any curvature in the code. The curvature at second order induces lots of new couplings between the multiples, makes everything significantly more complicated. And of course, all our observations so far point to curvature being small. The code does not have any massive neutrinos. Massive neutrinos make class significantly slower. And of course, the same would be true to a much worse degree for song. So it would be very interesting to have massive neutrinos. But of course, currently there's no real need to do it, because we have a signal to noise for the bispectrum at least, which is below 1. And then to make it a little more precise at a huge computational cost, we don't have any special interactions. Some of these may be very easy to implement. So in class, of course, there has been done a lot of work of taking the code and putting some new interactions in the code. The same can be done in song, and it may not be difficult. Just that with the current experiments, probably you cannot detect it unless you have some reason to believe that this particular interaction will greatly increase the non-Gaussianity. But if we get to the point where we have, where was the plot that I'm looking for? Yeah, if we get to the point where we have a prism-like experiment and the signal to noise of the intrinsic bispectrum reaches to some level of 2.5 or so, then of course it may become much more interesting to implement extra effects into the song code. But so far, the song really runs on a vanilla cosmology. Okay, that's essentially it. I just quickly wanted to already show the installation instructions so that you can preferably try today to install the code, and we can fix some of the problems tomorrow before we start with the song exercises. Okay, that's all I wanted to say for today. So I'll be happy if there are some questions to answer them. Yes. I think you have to release and then wait until it turns green. Yeah.
So could you please comment a bit on the physics which generates this early time second order effects?
You are talking in relation to the late time here.
No, early time really, like during the radiation domination or after combination. What is the physics?
Yes, as I told, for the non-Gaussianity or bispectrum in particular, here this equation tells you that all physics will generate bispectra. You don't have to pick up some specific second order term and say, well, this term gives me my bispectrum. No, all of them give you a bispectrum. So really the physics is everything that happens in the universe at second order. There's nothing. Of course, you can go through everything that happens at first order, and then the same to some degree happens at second order with additional sources. But there is nothing that you could point to and say, well, this is the part that gives the bispectrum. Okay, any more questions? Good. So I guess we are done for today, and